Hello folks, here's the video about chi-square I promised you. Now chi-square is a statistic that you use to work out if the results you get in an experiment are likely to have been produced just by random chance alone. So whenever you do a chi-square test, you always start with something called a null hypothesis. And the null hypothesis is always that your results have been produced by random chance, just random variation. So if you think about our woodlice in this experiment, we're putting them on a choice chamber. They can either go to one half or the other. Now that might be left or right, it might be light or dark, but if it is a truly 50-50 chance, you would expect the distribution of those woodlice to be kind of 50-50. So you'll have set out by doing a control experiment. Okay, so you might have collected just one set of results after a time interval there, or you might have taken a series of repeats over a couple of minutes or so, and you'll have counted how many were on the left and the right each time. Now what the chi-square is going to do is it's going to see, is it very likely that these results were produced just by random chance with no preference at all? So the chi-square assumes that the woodlice have got no preference for one side or the other. Let's take this set of results. It doesn't matter if you've got repeats, you can use them all, or if you've only got one set of results, you can just use that one pair of numbers. The calculation will work in exactly the same way. But here's what you're going to do. So I'm just going to take the number on the left and the right side, and I'm going to drop that into this table. Now I've set this table up to do the calculation for me. You won't have that luxury, you'll have to do it yourself, but the calculation is easy. So what I've done is I've put all of those numbers in there, left versus right. Remember, this is our control experiment, so we haven't tinkered with the light levels at all. What we are going to be looking at is whether or not these results are so outlandishly skewed that they couldn't be possibly due to random chance alone. So we have to compare our observed results with what we would expect to get if our woodlice were completely unbiased. Now, we took a series of observations of these woodlice, and we had 10 woodlice at a time. We took 6 observations, so there's 60 observations in total, which means that you'd expect to find 30 observations of them on the left and 30 of them on the right, if they're completely unbiased. What we've actually found is 27 on the left and 33 on the right. Now this is seeming to suggest that our woodlice have got a preference for the right hand side of the tank. But does that mean that they are significantly biased? Well, this is what chi-square will tell us. The formula's down here. This is chi-square equals sigma O minus E squared over E. Well, this is how it works. You first need to work out the difference between your observed and your expected results. And we do it by taking the observed and subtracting the expected. In this case, that's going to give us -3 for the left category and +3 for the right. We've got a negative number there, which is not ideal because when you do calculations with negatives, they tend to cancel positive numbers out. So what we're going to do is we're going to square everything so that we're dealing with only positive numbers. So this is O minus E squared. -3 squared is 9, 3 squared is 9, that's what we've got. So this number in this column here is kind of an indication of how far from our perfect unbiased 50-50 ratio we are. But the trouble with that is that the size of this number here kind of depends on how many times you repeat the experiment. If I'd repeated it another 100 times, well, I'd expect there to be a bigger gap between my observed and my expected, which means this number here would be a lot larger, even if my woodlice weren't any more biased than these ones here are. So what you do is you divide your O minus E squared by the expected value, and that's kind of like scaling it according to the size of the sample. So it doesn't matter how many repeats you do, your chi-square value will always be valid. So in this case, what I'm going to do is I'm going to divide 9 by 30. This is how I get my 0.3 for the left and 0.3 for the right. Now the sigma value means I've got to add those together. And the mathematicians amongst you will have realised that that's 0.6. So this number here is my chi-squared value, 0.6. And that's a measure of how far away from a perfectly unbiased 50-50 split, even split between the categories we are. You could do this if you had your chamber divided up into 4, only of course you wouldn't just have left and right, you'd have chamber 1, 2, 3 and 4, and your expected values wouldn't be 30 and 30, they'd be the total number of observations divided by 4 evenly, so 15, 15, 15 and 15. And you'd do exactly the same process, you'd add up your 4 numbers at the end and you'd get your chi-square statistic at the end of it. 0.6 doesn't on its own tell us anything. It doesn't tell me how likely we are to get this kind of distribution of results by random chance. In order to get that bit of information, we have to use something called a probability table, or a chi-square distribution table, and that looks like this. And at first glance it's horrible because there's loads of numbers, but in order to unpick which bits of this you're going to use, you need to think carefully about the experiment you're doing, and you're only going to be using one row along here. You've just got to choose it carefully. Now this column is labelled DF, that stands for degrees of freedom. That's like the number of choices the woodlice are faced with. So imagine the experiment. I take a woodlouse, I drop him in the middle of my choice chamber. He can either go left or right. He's got one decision to make. That woodlouse has got to be on one side of the chamber. So he's simply got a choice about which side it's going to be. So we'd call that 1 degree of freedom. If you divided your choice chamber up into 4, well, the woodlouse has got to occupy one of those. So if he's stood in one corner, 1/4, he could choose to be in one of the other 3. So that would be 3 degrees of freedom, which is this row here. But let's focus on my example, which is just a 1 degree of freedom, choice left or right. What I've just highlighted there are pre-calculated standard chi-square values. And those chi-square values correspond up here to probabilities. These little decimal numbers at the top are probabilities. So what that means is if I got a chi-square of 0.016, this one here, that corresponds to a probability of 0.9 or 90%. So if you get a chi-square value of 0.016, the probability of getting those results by sheer random luck alone, as opposed to any actual preference by the woodlice, is 90%, i.e. very, very likely. Now let's have a look at ours. I said I got a value of, 0.6. Okay, that's my chi-square value. So I've got to try and find where 0.6 would sit in this table. And we've got some very low numbers at this end, we've got some higher numbers over here. 0.6 is actually going to fit right in this gap between that probability and that probability. Well, if you look at those values, that's between 90% and 10%. Probably nearer the 90% end, though, to be honest. So what we're saying is the probability of getting the results I put on that table by random luck alone are somewhere between 10 and 90%, probably nearer to 90%. So that's very, very likely. It is very likely that this deviation from our perfect 30-30 split is due to random chance. So this tells me, because I've got a non-significant result, I've got a small value of chi-square, a very high p-value, okay, so my p-value is between 90% and 10%, that tells me that any variation here is due to random chance. My woodlice have not got a preference for the left or right side. You may find this for your control, you may not. Now if you don't find this for your control, if you get a really outlandish set of data with a very, very low probability of it being due to random chance, then maybe you've got some biased woodlice. You might need to think about how you would discuss that when you come to do your evaluation. Right, I'm going to change the labels on these now. I'm going to do light versus dark. And we're actually going to plug in some numbers to have a look at some experimental data. Okay, so this time I'm going to get a different p-value. So I've established my woodlice weren't biased. Let's have a look at the results. You might have done 3 trials. You might have done it for several minutes longer than this. But the principle is the same. What you can do is you could calculate a chi-square for the whole lot. So I could take each of these results and I could drop each of them in to the table, calculate the total number of observations on the light side, the total number of observations on the dark side, or, to save a bit of time, you could calculate a mean. Chi-square will work with that as well. So what I've done is I've put every single bit of data in there. You could, if you wanted to, calculate a mean for those and then do chi-square with that, but I'm going to do it with all of my raw data. Now I've got 180 different observations of woodlice in the course of my experiment. So if they have no preference, if they're completely non-biased, you'd expect there to be 90 in the light and 90 in the dark, but I don't find that. When I add up all of these figures here, I get an answer of 50 observations in the light side and 130 observations in the dark side. Now you don't have to be a statistical genius to figure out they're clearly favouring the dark side there, but Does that mean our woodlice genuinely like it, or is it just random chance? Is it just that random 50-50 choice of those woodlice occasionally skewing the results slightly like we had in our control? Well, I've done exactly the same calculations as before. O minus E, that's minus 1440, square it, 1600, divide that by E, 17.7 recurring, and add them together, and now I've got a chi-square value of 35.6. That's a really high number. Let's look at our chi-square distribution table. Okay, the highest number on the 1 degree of freedom row is 7.89, and that's for a probability of 0.5%. So my chi-square value is significantly bigger than that. We would say that I've got a really, really low probability of getting my results by chance. Therefore, I found a significant result. I found a preference for those woodlice. They much prefer to be in the dark. So there is a cutoff point. There is what we call a critical value. My p-value was less than 0.5%. Let's actually use the less than sign, shall we? So less than 0.5%. So that's highly significant. But what you do in most investigations is you actually use the 5% value as your kind of cutoff point. You have to have a probability of less than 5% to have found an actual preference. Scientists have chosen this fairly arbitrarily, but what it means is that, 1 time in 20, you might be wrong. You might think you found a significant value when you haven't, or vice versa. But 5% is a 1 in 20 chance. That's significantly unlikely. So this is what we call our significance value. So if I go back to the table, you can see that at 5%, that's this one here, p equals 0.05. The chi-square number that you get is 3.841. We'd call that our critical value. Okay, so at 5%, the critical value is 3.841. When you are analysing your woodlice to find out whether they prefer the dark to the light, you are going to need to find a chi-square value bigger than that to show a significant preference. Anything less than that is going to imply that there's quite a high likelihood of you getting your variation in your results just through random luck alone, and we can't put it down to the preference for light or dark. You've got to get a less than 5% probability to be more than confident that there is an actual preference there. My woodlice, while the p-value is less than 0.5%, we're really sure. You might not get a significant result in this experiment. Some people found that the probability of getting their distribution by random luck alone was 10-15%. So although it may look like those woodlice are favouring the dark side, you can't say with any degree of certainty that they are. And you would talk about that in your results. You would give your p-value and you would say, look, this is not a significant result. We can't be certain that woodlice prefer one side or the other. Okay, I hope that was in some way useful, and I hope you can use some of that in your write-up.